Guwahati. She'll be telling us about on the p-rationality of consecutive quadratic fields.
Thank you so much for the introduction. So, so thanks a lot for the opportunity and this platform. So I'll be talking about p-rationality of quadratic number fields. And this is based on a joint work with Dr. Chattopadhyay and Professor Anupam Saikia. So the talk will go in this way. Firstly, I'll define what is a p-rational field. Then I'll talk about Greenberg's work and conjecture on such fields. And then I'll proceed towards some criteria that describe quadratic p-rational fields. And then our work, which is based on consecutive p-rational, both real and imaginary quadratic fields. So suppose K is a number field, and let us say that P is a prime number, and suppose MP be maximal p-ramified Pro-P extension of K, and let gal M over K be the corresponding Galois group. We say that the number field K is p-rational if the Galois group is a free Pro-P group. So throughout this talk, we'll be dealing with the algebraic number theoretic aspects of field, like regarding the class numbers, fundamental units, etc. So this concept first arises in Moavedi's thesis in connection with the number fields that satisfy Leopold's conjecture. And in 2016, this resurfaced when Greenberg was studying the continuous representations from the Galois group of M over Q to GL and Z. So this M is same as the M that I've defined earlier. And he concluded that whenever the number field K, the one with which we began with, whenever that is p-rational, the representations will have open images. And according to Greenberg, one suitable choice for a narrow field would be some multi-quadratic fields over Q. And on that spirit, he conjectured that for any odd prime P and any integer T greater than or equal to 1, there exists a p-rational number field whose Galois group over Q is isomorphic to the direct product of Z by 2Z T many times. So if we see the state of art of this conjecture, Barbulescu and Ray had proved that Q of root P square minus 1, this is p-rational for all P, so proving the conjecture for T equal to 1. And Benmarim and Mohavedi showed that Q root of P into P plus 2 and root of P into P minus 2, this is p-rational for all P greater than or equal to 5. And in case of P equal to 3, they showed that Q root of minus 1 adjoined with root of 3 is p-rational. So the conjecture has been settled for T equal to 2. And comparison showed that if we adjoin root of minus 1 to this quadratic biquadratic field, the resultant triquadratic field is p-rational for infinitely many. So the conjecture is still open for T equal to 3 and higher values. So we'll be dealing with abelian number fields, and for such fields, Greenberg had shown that for a number field K which is abelian over Q, and if P is a prime number such that it doesn't divide the degree of extension, then K is p-rational if all the subfields of K, say L, such that they're all cyclic over Q. If all such fields are p-rational, then K is p-rational and conversely. So in particular, if we substitute K with some multi-quadratic field over Q, then we can clearly see that the subfields over K of subfields over Q of K, which are cyclic, are just the quadratic fields. So this shifts our interest towards studying the p-rationality of quadratic numbers. Now, if we proceed to quadratic number fields, Greenberg showed that whenever P is greater than or equal to 5, and whenever P is 3, it must be unramified. Then in these cases, if K is a real quadratic field, then it is p-rational if P does not divide the class number of K. And secondly, the fundamental unit of K should not be a pth bar in any completion of K with respect to the primes lying above P. And in second case, if it is imaginary, it's just enough to show that P does not divide the class number of K. These are both necessary and sufficient conditions. Now let's see a quick example. If K is Q root of minus P, then we can use Hua's bound for class numbers which involves root of discriminant and log of root of discriminant. Since the discriminant is going to be at the most 4p, and for p greater than or equal to 5, we have omega k, which is the number of roots of unity in k as 2. We can show that the class number is strictly lesser than p for sufficiently large primes. So after a certain stage for all primes, the field of the form q square root of minus p is going to be p-rational. Now I'll proceed to another conjecture given by Lizuka, which says that for any prime number L and integer k greater than or equal to 1, there exists infinitely many d in integers such that the fields q square root d, square root d plus 1, q square root d plus k, all these k plus 1 fields have their class numbers divisible by L. So if we observe the primitive elements, these are all consecutive integers d, d plus 1, so on till d plus k. So on the lines of this consecutivity and p-rationality, so p-rationality deals with the indivisibility of class numbers. So if we try to connect these, we ask the question that given any integer k greater than or equal to 2, can we find infinitely many primes p such that there exists k consecutive, real or imaginary p-rational numbers? So once again, consecutivity means the consecutiveness of the primitive elements. So we could answer this question affirmatively for any k in case of imaginary fields and for k equal to 2 if the fields are equal. So the first result involves imaginary quadratic fields. We showed that for any k greater than or equal to 1, the fields of the form q root of minus p minus 1, q square root of minus p minus 2, so on till q square root of minus p minus k are all simultaneously p-rational. And also there exist infinitely many primes p such that the fields of the form q root of minus p minus 1 in q root of p minus p into p minus 2 and so on, they are also p-rational. Now when we go to real quadratic, we showed that q square root of p square plus 1 is p-rational whenever p square plus 1 is square. And similar result holds true for q square root of p square plus or minus 2 and q square root of p square plus 4 as well. Also, we could show that there exists infinitely many primes p for which all these values are simultaneously square p, making all these 4 fields simultaneously p-rational. So I'll go to the imaginary quadratic fields. So let us name our fields. So ki denotes the field q root of minus p minus I, and fi denotes the field q root of minus p into p minus I. So since these are imaginary, the criteria was simply the indivisibility of class number with respect to p. So instead of showing that, what we try to show that the class numbers are strictly lesser than. And for this, we will be using Logotin's bound for class number, which involves again the number of roots of unity, root of the discriminant and log of the discriminant. So the idea is that if we can sufficiently shrink the size of discriminant in terms of p, then we might be able to achieve that the class number is strictly lesser than p. And in order to do so, we showed that there exists for any k, there exists infinitely many prime numbers p such that all the numbers p minus 1, p minus 2, so on till p minus k have large square factors. Large in the sense that the square factors are of value at least log of p square. So for this, we use the result by Anand Chattopadhyay and Roy, which says that for any m greater than or equal to 2, there exists a polynomial of this type, such that all the pi's that are occurring, they are all mutually pairwise co-prime. And using this, we could show that for any large interval, like involving a large quantity x and any k, we can find mutually co-prime integers m1, m2 up till mk, such that all of them are co-prime for the LCM of 1 to up till k as well. Then using Chinese remainder theorem on this system of congruences and using the Dirichlet's theorem for primes in arithmetic progression, we could show that given any real number a greater than 0 and any finitely many integers r1, r2 up till rs, we can find infinitely many primes p such that p minus ra, all of these p minus ra have a square factor greater than log p to the a. For our result, we can take our a as 2, and instead of taking r1, r2 to rs as any integers, we'll be taking 1 to up till q. So using this result, we could show that the class number is strictly lesser than is lesser than or equal to root p by log p, which is strictly lesser than p. Similarly, for the other family as well, we could show that the class number is lesser than p, answering our first question. Now let's move to real quadratic fields. Benjamin and Moorley showed a special criteria for p-rational number fields, particularly when p is unramified. So for that, they defined the generalized Fibonacci number in terms of the fundamental unit. So if epsilon is the fundamental unit of a real quadratic number field k, then they defined the Fibonacci number as epsilon to the n minus epsilon inverse to the n divided by the difference of epsilon and epsilon inverse. And the first term of the sequence, they defined it as 1 and the second term as well. So we'll be calculating this value at a particular number, which is q, which is p to the f, where f is the residual degree of p in k. And since we are in quadratic setup, the value of f is going to be either 1 or 2. So q is either p or p squared. So under this notations and setup, they had shown that the real quadratic field where p is unramified, it will be p-rational if the class number is indivisible by p, and the Fibonacci number calculated at q, which is going to be either p or p square, that must be incongruent to 1 mod p square. So for our field, which is root p square plus 1, p doesn't divide the discriminant, so it is unramified, and p square, for now we'll assume that p square plus 1 is square root. And the fundamental unit of this field looks like this. So if we calculate the Fibonacci number at both p and p square, we found out that using binomial theorem, we first expanded the terms and then taking mod p square, we found that mod p square fq is either p or 0. So in both the cases, it is incongruent to 1 mod p square, satisfying the second criteria. So we are just left to show that the class number is indivisible by p. So here in this case, we'll be using Dirichlet's class number formula and Logotin's bound for L1 chi k, which says that it is lesser than log tk plus 2 by 4 whenever 2 is ramified. So using the property of log, that 2 log x is log of x square and the previous inequality, we could show that the class number is strictly lesser than this fraction. And using the fact that root of p square plus 1 is greater than p, we could show that the denominator is greater than log of 16p to the 4. So if we take the reciprocal and use the first inequality, we could show that the class number is lesser than this whole sum multiplied with root of p square plus 1. So for large values, root of p square plus 1 is close enough to p. So if we can show that the sum inside the bracket is sufficiently lesser than 1, then we'll be done. And for that, we can observe that log 4p square plus 1 divided by log 16p to the 4 is almost equal to 1 by 2. And if we see the second term as a sequence in n, this converges to 0. So for large prime numbers, the second term, like we can make it sufficiently smaller than 1 by 3. So combining both of these, when multiplied with root of p square plus 1, this becomes lesser than p, satisfying the first criteria as well. So with both of these, we could show that k is p-rational. Now everything works well if p square plus 1 is square root. So in order to prove that there indeed exists infinitely many p, we used a result by Heath-Brown for irreducible polynomials of the form x to the d plus c at prime arguments. So according to this result, Heath-Brown found the density of primes p for which such polynomials are square p. So in our case, the polynomial under consideration would be x squared plus 1. So we could show that the density is at least 0.834. So there are infinitely many primes for which p squared plus 1 is square root. And we could show similar result for the field q root of p square plus or minus 2 and q root of p square plus 4 as well. Also using the same result by Heath-Brown, we could show that there exists infinitely many p such that all the 4 values are simultaneously square, making all the 4 fields simultaneously p-rational. So if we see q root of p square plus 1 and q root of p square plus 2, they act as consecutive fields. And also by a result by Barbulescu and Ray, as I stated earlier, q root of p square minus 1 is p-rational for all p. And here we have shown that q root of p square minus 2 is p-rational for infinitely many p. So we find another family of two consecutive fields that are p-rational. So these are the references. The second paper involves the result by Barbalescu and Ray, where they showed that q root of p square minus 1 is p-rational. And our work is based on the fourth paper. And the third paper involves the work by Moadi. And this is the paper by Greenberg, where the concept of p-rationality resurfaced with all the criteria. And this is Mohavadi's thesis, where it was initially originated. So, yeah, thank you so much.
Any questions? Speaker.
The imaginary quadratic case that you try to get this also when these p plus i's are in use square free.
Yes, we can do that. No, like for p plus I and in imaginary quadratic case, like find the main q root of minus of p plus I, right? Yeah, so in that case, if we just replace our result here, yeah. So in place of 1 to up till k, if we replace by minus 1 up till minus k, we can show that there exist infinitely many primes for which all the p plus I have large square factors. So we can like shift our result towards the p rationality of q root of minus p plus I as well, if that is what you ask. Yeah.
Whether you can arrange this when this p plus r is almost square free. So you arrange it by the large square factor.
Yes.
But without the square factor, you can't do it.
No, because the idea was to shrink the size of discriminant. So square freeness may not help in that case.
Any further questions? People online, any questions for the speaker? See any questions online or any more in the room? And let's thank all the speakers.